Hello, dear friends. Today's lecture is about the models of mixtures of distributions and their possible applications. We will consider a model of mixture of distributions, starting from just a model of distribution in parametric and non-parametric forms. And there we will consider the possible applications of such a model. After that, we will consider the multidimensional case and possible applications of the models corresponding to this case. Now we will start with the parametric and non-parametric models of distributions. The starting point for such a model can be the picture of Antoine de Saint-Exupéry, Le Petit Prince. You can see it on the screen, and it can be associated with the hat. This hat can be considered as a picture of unidimensional parametric distribution, as you remember from this novel. This picture was associated in the eyes of adult people as a hat. In the more advanced side of children, it's a snake. It's an elephant inside the snake. It's much more complicated picture, and it can be associated with the parametric model. Using parametric approach, we know what we deal with, and here we deal with the particular object. We know just everything about this object, but the parameters of it. So we can estimate the parameters, and the picture will be completed. This association, I think, is very useful to recognize the parametric and non-parametric approach. To create the parametric model, we need the non-parametric model first, and then we need additional knowledge about the nature of the phenomenon we are trying to model. The scheme of parametric modeling can be presented as follows. We analyze the empirical distribution using non-parametric model. It sounds like oxymoron. We create the parametric model, but use non-parametric model first. But it's there is no contradiction in this statement, because we need the general appearance of the distribution. After that, we should be specific about the nature of the phenomena, and we can assume the type of possible distributions on the base of this theoretical analysis. After that, we create the model or models of distributions. The plural, in my case, can be associated with a few models which can be compared, and we try to test the hypothesis of the model's relevance, and using the particular criterion, we can choose the best one from these competitive models. Let's get started from the non-parametric model, which presents us the general appearance of the distribution. Here you can see a unit-dimensional scatter plot, which presents the cases we see in the case of unidimensional feature, or unidimensional characteristic. We are interested in the density. We try to create the picture of density. The more the high is the density, the high is the height of the particular rectangular. You know the picture of in this slide, a picture of histogram, which is well known to all the statisticians, from beginners to advanced users of statistics. You can see that this picture, using one more dimension, shows us the picture of density. I associate this style of density presentation with the cubism in the art. It shows us the rough picture using the particular instrument by an artist. There is a trade-off between bias and variance in creation of such picture. If we take the particular criterion to create the best choice of the bin width in this histogram, we can see that using integrated mean-squared error, we deal with two elements in the sum of this criterion. This is the variance and the square root bias. And the trade-off is between these two components of the integrated mean-squared error. The key point here is not the great amount of formulas you can see here, and we can find it in the David Scott's article, 1980, and you can easily find it on the internet. But the most interesting thing here is that we need the unknown probability density function g of x to create the best possible picture of probability density function. It's like a dog chasing its tail. To create the best picture, we should know in advance what we are talking about in details. So to make it real, we should avoid two opposite situations: over smoothing and under smoothing. We will talk about some later. And now there is one more interesting point. The starting point for creating the histogram. If we use one starting point to create this histogram, we have the particular shape of it. If we use some shifted starting point, we can see another shape of the histogram, and so on. To avoid the influence of our choice for starting key point, David Scott proposed the average shifted histogram, which presents us the particular histogram. You can see it at the lower part of the picture. And if we make the constant shift of the starting point after taking the average value for the density at each point, we come to the kernel density estimate with the rectangular kernel. There are different kernels which are widely used to create the kernel density estimate of probability density function. The most well-known are rectangular, which was mentioned above, and also they use the triangular form of kernel density of the kernel, the Epanyshnikov and Gaussian kernels. These kinds of kernels are well known and widely used in applications. As I said, we should avoid two situations of undersmoothing and oversmoothing. The oversmoothing picture is at the upper side of the slide. The undersmoothing is at the lower part. And Silverman's rule for simple distributions is presented at the right side of this slide. You can rely on this rule at the preliminary analysis of the density, and then you should be more particular in your choice, trying to follow the rules I talked to you during the previous time. So sorry. And now we are talking about the nature of the phenomenon. We will take in account when you try to consider the particular type of your model, when you create the specification of your model. Here is one of the examples. Each example corresponds to the particular feature, and for this case, we can consider the income, which is the product of three multipliers. The first one is the earning of the household's head. The second is the particular multiplier for this first component, and the third one is also one more multiplier. And the first one is in turn can be is presented by the product of other possible multipliers. We should take into account that the income is a product of different multipliers, and it helps us to consider that this model, the model of income, can be presented in the form of logarithm, log normal distribution, because if we take the logarithm of income, we come to the sum of logarithms of the multipliers. So, following the central limit theorem, we can propose that the probability density function for homogeneous group can be log normally distributed, and the model of probability density function for log normal distributions are presented here, and if it can be associated with our model of general appearance of this distribution, especially it's much more convenient to consider the probability density of the logarithm, taking into account these both proposals, these both arguments to create the model of log normal distribution, we can create the specification of such a model. An important question: we consider variables of different types: directly measured feature, subindex based on the few directly measured features as a linear combination of the directly measured features, and overall aggregate index, which aggregate the subindices, which is in turn the linear combination of subindexes. Which variable from the set above generally is more likely to be normally distributed? It's a good question. Try to make your answer, and after a pair of seconds, I'll give you the right answer. The answer is the overall aggregate index is the best the best representative of the normally distributed value, and it can be associated with such kind of distribution because of the restrictions of central limit theorem. That is why the indices which are widely used in practice we consider as normally distributed. After that, I'll extend the initial model to the model of mixture distributions. It can be associated with the reconstructed picture of Antoine de Saint-Exupéry, and inside the snake there we can consider not the only elephant but a pair of elephants, or 3 elephants, and so on. But we have the reasons to such a specification of the model. The parametric model of a mixture of distributions can be presented as follows, where Q sub j are the weights of each components in this mixture. The sum of Q sub j is a unit. So the overall model can be presented with a dotted line here in this picture. And its components are above this dotted line. We can see three components in this mixture, in this example. And in the scale, and when we use the horizontal axis presenting the initial feature, we can see the mixture of log normal distributions. It's less convenient that consider the distribution in logarithm scale, but to make clear how it looks in the initial scale, I presented it here. Our task is to estimate the parameters of the mixture of these mixture distributions. We use maximum likelihood estimation, and this estimation gives us the vector of the parameters, which includes the weights of the components and the parameters of the central tendencies of each component and standard deviations of the components. So we deal with numerous parameters here. In the table, you can see that our model has 9 parameters, and the good question will be how many parameters we should estimate using the approach of it was presented at the previous slide, using the maximum likelihood method. The right answer is that we should estimate 8 parameters, because as I said, the sum of weights Q is equal to a unit. Automatically can be calculated one of these values by the subtraction from a unit to estimated values of weights. Here you can see one of the examples. We will consider it some later in details. And you can see that the maximum likelihood estimates gives us the clear picture of the structure for this case, and the overall population can be presented in the form of a mixture of 3 subpopulations with the different characteristics of their central tendency and spread, with different spreads. And if we take into account the multi-dimensional case, we can see that normal distributed value can be presented in more more complicated form, but we can also use the kernel density estimation to create the model, non-parametric model of probability density function. And you can see here at the left picture, the over smoothed kernel density estimate, under smoothed the effect of under smoothing is in the central picture, and at the right picture you can see as I can see, the best kind of model which avoids the effects of under smoothing and over smoothing. And we can consider a pair of 3 components on this color, which is associated with a 3D model of probability density function. The number of the parameters is much greater in this case because except the central tendencies, which can be presented as a 2-dimensional vectors, according to the dimensionality of our feature space, we should use the correlation between these features for each component. So we deal with the great amount of parameters to be estimated, and we need much more cases, much more observations to estimate these parameters. As you know, we need about 5 from at least 5 from 5 to 10 as usual observations per one parameter to be estimated. Here you can see the histogram, 3D histogram, 3-dimensional, which presents us the probability density function and its non-parametric estimate in the form of a 3D histogram. In 2 dimensions, the mean income of the households and desired income is one more feature, and in this feature space of desired income and the real income, we can see 2 components. These components may be presented in the horizontal space in different type of histogram. As I remember, I had this picture. Maybe it's can be presented some later. And now, what should we do with such models? The applications can be different. The first one is the crisp and soft classifications. Crisp classification is a traditional type of classification using the Bayesian criterion of mean risk over the classification. We should use the loss function here, and a simple loss function is the best choice in this case because we deal with the nominal scale of the names for each possible component. And applying this simple loss function, we create the rule for this classification. The rule gives us the choice for associating the particular object with the component in our model. This rule says that for the particular value of x, we should put it in the corresponding bin when its weighted probability density function is higher in comparison with the other weighted probability density functions. So if we if we consider the value of feature sum left from the vertical dotted line, we should associate it with the first component in our mixture to the right from this vertical dotted line with the second stratum, and to the right from the second vertical dotted line with the third stratum. So it's the kind of membership function for three strata, and we can see the rule in the form of picture. For soft classification, it can be presented in another way. We calculate the ratio of weighted probability density function and the sum of probability density functions of all the strata, and after that we can calculate the membership function for each stratum. So the corresponding object with the value of x sum left from the vertical dotted line, we should put it, it can be associated with the first stratum with the membership function sum greater than half, with the second stratum sum lower than a half, so it belongs to really to two neighbor strata, but to the first its membership function is sum greater than to the second one. So we can use more complicated form of classification, but it can help us to create the models which in some cases may be more adequate to the situation. Coming up to the previous example with probability density functions with three strata, we can make the portraits of the components. The feature we considered in this example is really the logarithm of the salary for the university staff. And the portrait shows us that they are different in the aspects which are outside of this feature, the relation to the university scientific degree and academic rank, which are the we consider as determinants for the description of the groups, the features of the groups, which are the determinants for such stratification of the staff, university staff. And these portraits may be presented in different pictures and different graphs. And we can see the difference between soft and crisp classifications here. The results of these classifications. And now we can consider the one more application, typological regression, which can be based on soft classification. This case is about distribution of Russian regions on the expenditure on research and development. It's the vertical scale and of this feature. Sorry, the horizontal axis, the expenditure on research and development in the dozens of Russian regions. We can see here three strata. These strata are presented in the map, and we can see where are the regions which correspond to three strata here. We can create the model based on crisp classification rule, traditional classification, and soft classification. And we can create the regression model for each stratum, and the models will be different after crisp classification and after soft classification. In the more advanced model of soft classification, we can see that the additional determinant, the additional regressor, which presents the additional feature which shows us the role of small enterprises in the research and development. So it's more complicated and more adequate, more informative model in comparison with the more simple case. Let's come to the mixture of distributions in their multidimensional case. Multidimensional case is much more impressive. It can be presented in different forms. In 2D, two-dimensional scatter plot, it's easy to recognize the points here. The case with the high dimensional space needs additional form of presentation using colors, maybe the cases may be more bright or less bright. And here you can see the multidimensional distribution, 3D, which use not only the position on two-dimensional space, but the color as an additional additional dimension. In two-dimensional, in the heating map, we can see the kernel density estimate of probability density function in heating map, which probably consists of two components here, and we can present it in the form, the particular form. I said in advance that we can slice this previous picture by horizontal planes and present here the distribution in such a form where the X scale presents us the desired income, and vertical axis is the real income of the household. And we can see that the households with a high income is of another nature with respect to the correlation between real income and the desired income. They are quite independent from each other. And for lower income part of the population, we can see the correlation between real income and the desired income and real income. They may be described as the correlation between these two important features and the absence of this correlation for the high income part of the population. This case is, I suppose, is interesting. We also created the model of regional structure of the country on costs and results of innovation activity. In the case of Russian Federation and the picture of two-dimensional probability density function looks like the figure which you can see here on this slide. We can create competitive models. In the three-dimensional case, you can see how many parameters we should estimate relying on our data. Here we can see that we have 6 parameters for each stratum, for each component, and the overall parameters to be the overall number of the parameters to be estimated is not 18 but 17, because one of the sum of weights is equal to a unit, as you can see here. So one of the parameters of these values is not independent. So 17 parameters should be estimated. And in the two-dimensional scatter plot, we can see these regions of Russian Federation. And we can see, we can create 4 different models. The first one includes just one component. Just one component with the center, which is pointed here as a black point. It's the central tendency in two-dimensional case. The overall distribution, it's like hill, which is extended from at the direction of diagonal direction. The second model can be presented in the form of two components, the first one and the second one, and the three-component model. And also we can create the model of four components. Which one to choose? It depends on the value of the criterion for each case. You can see here the results of identification for each of these models. The first one includes the only component with the weight of this component a unit. It's evident, and with the positions you could see at the previous picture. The second is the model two-component model with the weights some more than 1/5 and 4/5 for the second component, and it is associated with this picture. The third model associated with this model, with this case, this model, and the most complicated is the fourth case. For each, we should use the information criterion. We used two criteria. The Akaike information criterion and the Bayesian or Schwarz information criterion, in which are presented with the red line here and blue line. The lower is the value of each of these criteria, the better is the model. And we can see for both criteria, the best choice is the model with three components inside. So it's the trade-off between complexity of the model and its information power. It's a good example which is completed by the choice of the models which are competitive with respect to each other. And now I should demonstrate you how we can calculate using just a simple, relatively simple soft Excel to create the model of the probability density functions. It was created before it could be used when we apply the more advanced software like R or Python. This example was created before this before they was introduced for the population when they will not exist at all. And now you can use this one or maybe more advanced software which allows us to create such kind of a model of mixture of distributions. The first point is the kernel density estimate of probability density functions with different kinds of the kernel. Triangular, rectangular, or Yaponichnikov, and here on this slide, dotted line gives us the kernel density estimate with the Gaussian kernel, which is much more the better smoothing line in comparison with the cases of other kernels. So if we try to describe the density, probability density function as a the component with one component model, unicomponent model, we can see that it's not the best way to present the model of distribution. We can rely on the statement that we deal with the only component and try to estimate the component, minimizing the maximizing the likelihood criterion. You can see it here. It is calculated according to the as a sum of logarithms for each case of the probability density function, logarithm of sum of logarithm of probability density functions for each case. And here we can see that we deal with the only component here. It has a weight of a unit and the corresponding value of the central tendency here, 10.5. It's the center of this distribution, and the spread associated with the standard deviation, which is 1.5. We can calculate the best choice of such components and try to obtain the best model in this specification. But using more advanced model, we can come to the two-component models and present it here. One second, I'll try to do it right now with you. And in this case, we can consider that we deal with the two-component model. We will put here a half, for example, as a weight for each component, and a half with a different position of the central tendency. Let it be 9.8, for example, 9 point comma here 8, and for the second one 11.5. And the particular value of standard deviation should be applied here. It will be a unit for each component. And we can see the model which is associated with this case. We can improve it using the solver. Let's do it. I'll try to do it. Sorry. gives us the opportunity to do it. I hope. 1 second, but it's not easy to do in this case because we can't see the list. Oh, here you are. And it's not case of data, sorry. Using Zoom, it's not easy to do. But I'll give you an example of doing it using solver for 3 components. You can see that after using the solver to find the best, to calculate the best values of the components, we should estimate not 9 parameters, but 8 parameters, because one of them is linear dependent from the weights of 2 previous components. And we can see that we deal with a 3-component model here. It's the best choice in this case. And the parameters give us the opportunity to estimate the peculiarities of each component in the whole population, in the case of 3 subpopulations. This example I presented to you in my presentation, and it looks the path of creation of this model looks like this. You can do it now in R or in Python. It's easy to do, but in much more complicated cases, you can use your own software. You can create to obtain the model of the probability density function. Let's come back to the lecture and finish with the list of recommended literature. We presented in the author among with my co-author, we presented in different conferences, in different articles, and here you can see a few articles of the scientists devoted to the problems we considered at our lecture. I think you enjoyed the way how we can make different models in the form of a mixture of distributions. You could see the examples of different applications of such models. The ways to do it are different, and I think you will take in account the possibilities and the features of these models. Thank you for your attention.